Okay, so we are going to continue. Just a quick reminder about what these codes are. I mean, I've been emphasizing the vector space view, the linear space view. So you might want to think of codes as subspaces. That's a good thing to view about. That's a good idea to keep in your head. But you should also remember that these are discrete objects. I mean, there's only a finite number of them. Okay, so oftentimes when you think of planes, you think of a plane in 3D, there are an infinite number of planes, right. So many of them, and same thing holds for subspaces in Rn. Okay, but these are just finite objects. There is also a more combinatorial or discrete way of looking at it, which is also equally important. Okay, so just to emphasize that, I am going to ask a few questions, very simple questions, just to make sure you also view them as discrete objects and not just as spaces. Okay, so here's the example. I'm going to put it as an example, but basically a bunch of questions about what these codes are. Okay, so suppose I fix n equals 6. Okay, remember f2 6. Okay, so it's a vector space, all right. It's a 6-dimensional vector, but how many vectors does it have? Yeah, exactly 64. So that itself is finite. Okay, so if I think of codes inside this finite vector space, I only have a finite number of them. There will be a finite number of there will be only finite subspaces also. Okay, so you will see how it works. So suppose I ask a question. Okay, suppose I fix k equals 0. Okay, and then I ask you how many 0 codes are there. Okay, how would you answer that? That's a very easy answer. There is only one code with k equals 0. What is that one code with k equals 0? Yeah, there is only one code, and that is simply this guy. Okay, so there is only a single code with k equals 0. Okay, so that seems like a simple enough answer to give. Okay, but what about k equals 1?
K equals 0, are we sending any message bits at all?
Yeah, k equals 0 is a bad idea. Just to emphasize that it's a pure combinatorial object. I think definitely define a n 6, 0 code. It is an object, it has only 0. It's definitely not a very nice, it has no engineering significance. Okay, what about k equals 1? Okay, there are 2 code words in each code, but my question is a little bit different. I am asking how many 6, 1 codes are there?
63.
We can take 0
that is the
and
correct
then
answer.
63.
Okay, 63 is the correct answer. There are 63 different codes with k equals 1. Why does that answer make sense?
We can pick any one.
Yeah, so you have to think of the generator matrix. Okay, always go to the generator matrix. How many different generator matrices can I have for a k equals 1 code? Okay, so what is the generator matrix now? It's simply k equals 1 and n equals 6. You just have to pick one vector. Okay, one non-zero vector. Okay, how many non-zero vectors are there in f2 6? 63. For each such choice you will get technically a different 6, 1 code. Is that okay? Okay, so there are 63 6, 1 codes. Okay, so now suppose if I say I want only codes that are not equivalent under permutation. Okay, right, not equivalent under permutation is what? Yeah, exactly. So how many different k equals 1 codes will I have which are distinct even when I include permutations?
1, 2, 3, 4, 5.
So remember, when I have a G, I can do column swaps
6.
and not really change the code. Okay, suppose I say I don't want that to happen, what should happen?
6
The different number of ones.
Yeah, you cannot have the same number of ones, right? Any two non-zero vectors that I pick here with the same number of ones will be equivalent under permutation. I can simply do the permutation, get away with it. Okay, so I have to have different number of ones. How many different vectors are there with different number of ones among? If you have 6, exactly 6. You can have 1 or 2 or 3 or 4 or 5 or 6. Okay, only 6 of them are distinct from a permutation equivalent point of view. Okay, so 6 that are non-equivalent Okay. So, of course, under permutations. Okay. So, this I think is, I mean, the reason why I am doing these simple questions is to give you an idea of how. Okay, you tell me, is it 6 or 5?
One
The
one.
first bit is the message.
Okay. Okay, so what is this 6 first of all? Not saying 6 is not the number of bits, it's number of different codes. Okay, there are 6 different codes. Okay, so what are the 6 different codes? Okay, there'll be 6 different generator matrices. Okay, the first generator matrix will be what? 1 followed by 5 zeros. The second one will be 1 1 followed by 4 zeros. You can also take a variety of different things here. How many different can I take here? I mean, instead of G1, how many others are possible? 6 other G1s are possible. How many other G2s are possible? 6 choose 2, that would be 15, right? 15 different are possible. What about G3? 1 1 1 0 0 0, and then G4 likewise, right? So, you have a G4, G5 and a G6. Okay. So, these are the 6 codes which are not equivalent under permutation. Okay. So, these are different questions that you can ask in a binary vector space which does not have an equivalent in the real numbers. Okay. So, there is no reason why you should ask such questions in the real numbers, but in the binary vector space there are nice questions like this that you can ask. Okay. These are essentially combinatorial. Okay. So, a question like this you can imagine becomes much more complicated if I say k equals 2. Okay. Right now k equals 1 becomes easy enough, everything is simple. If I say k equals 2, what will happen? So, you have to pick 2 linearly independent non-zero vectors. Okay. So, the first answer is actually not very difficult. Okay. So, in fact there is a formula that is well known for nk. Okay. So, if you have k equals 2, what will be the formula? The first vector you can pick as any non-zero vector, the next one should be linearly independent of that. Okay. What is the only linearly dependent vector? Same. So, you pick any one from the 62, right? So, 63 into 62. Is that enough, or am I making some mistake here? Should I divide by 2 to reduce the row choice? Yeah. So, you have to divide by 2 to get a better number. Okay. So, there is a formula like that in general. Okay. But it's eventually it becomes more and more complicated. Okay. If I ask a question about non-equivalent codes for 6, 2, it will become a little bit more complicated. Okay. So, those are combinatorial questions about these codes which are more difficult to answer. Okay. I am briefly mentioning it, we will never get back to this in this course, just writing it down so that you are aware that there are other ways of viewing codes than just as subspaces. Okay. They are also equally interesting, they have very challenging problems in that area also. Okay. So, let us move on. The next important and probably the most important attribute of a code is what is called minimum distance. Okay. Of course, n and k are important. Okay. So, nobody can say n and k are not important, but n and k are in a way easily computable. Okay. So, n definitely is very easily computable, k is also easily computable. Gaussian elimination is not a very complicated operation. After all, at most it can be n power 3 or something in complexity, that is not very difficult. Okay. So, you can compute it. So, minimum distance is a property of the code which is not easily computable. You can show it's what is known as NP complete, etc., etc. So, it is a very difficult thing to compute. Okay. But nevertheless, it is one of the most important characteristics of a code. So, as you can imagine, the most important characteristic is not easily computable. Okay. So, that's how all problems in engineering are. Okay. So, you have to get used to it, but let's see what the definition of this is. Okay. So, suppose I have a code C. Okay. So, let us say we take nk code C. Does not matter, this n and k are not so important for the definition. Okay. The minimum distance usually denoted d denoted d is the, okay, so let me write it out differently. Okay, I will also introduce the notion of a Hamming distance soon, I mean as in this definition it will come, but let us do this. Minimum over u comma v in C, u not equal to v, what is known as the Hamming distance between u and v. What is dh of u comma v? So, dh of u comma v is number of places in which u and v differ. This is the definition. Okay. So, this is the minimum distance. Okay. So, just looking at it, it seems like, why did I say it is hard to compute? It does not make any sense. It is just, what am I saying? It's, after all, I am doing a very simple computation here. Why is it hard to compute? Which part of it is hard and which part of it would be easy in your opinion? Okay. Given a u and v, finding dh of u comma v is not that hard. Okay. So, it's the complexity is of order n. Okay. So, you have to do n different operations, you can compute it. Okay. But what is the difficult part? Over all possible u and v. Okay. So, how many possible u and v do you have? No. Oh, u and v are in C. Okay. It is not. So, let us be very careful about how difficult this problem is. Yeah. So 2 par k, choose 2. That is the total possibilities, which is going to be exponential in k, exponential in n. Okay. So, it is not going to be polynomial, and you can't do it very easily. Okay. So, that is the problem essentially. Okay. So, u and v in C are going to be 2 par k, choose 2, which is a fairly large number. Okay. So, the number of different comparisons you have to do is very large. Okay. So, this, it turns out the 2 par k, choose 2 can be reduced to 2 par k itself. Okay. I will show you how that is done. It is a very, very simple, I am sorry. Yeah. So, I am going to derive that next. It is a very simple step. We will do that first and then we will proceed further. Okay. So, first of all, this distance, if you have not seen it before, can be a little bit confusing. Okay. So, the Hamming distance, what is called the Hamming distance? It is called the Hamming distance. Okay. So, this is called Hamming distance after Hamming, Richard Hamming, who can be considered as like say the father of codes or something like that. Okay. So, it is a very guy in the 50s was active. Okay. So, let us see a few quick examples of this and then we will proceed further. Okay. So, suppose I say dh of, let us say 0 1 0 0 1 1, this would be what? 1. Okay. So, and then dh of 0 1 0 1 0 1, this would be what? 3. Okay. So, these are the kind of examples. Okay. So, one relationship which is very useful for Hamming distance is the following: dh of u comma v is the same as what is called the Hamming weight of u plus v. Okay. So, what is wh now? To define what wh is, this is called the Hamming weight the Hamming weight is slightly simpler than the distance. Okay. Suppose you have wh of x, this equals number of ones in x. Okay. Okay. So, this is the weight of a vector. It's called Hamming weight. Oftentimes Hamming is dropped. Okay. Same thing with Hamming distance also. This distance and weight are basically Hamming distance and Hamming weight. Weight is the number of ones in a vector, and this relationship is very, very easy to prove. Okay. Number of places in which u and v differ, if you do an XOR of u comma v, what will happen? Wherever there is a 1, u and v differed in that place. If it is 0, then they did not differ. You simply count the number of ones in the XOR, which is the weight, you get the answer. Okay. Now, this relationship can be used to decrease the computations needed in the minimum distance computation a little bit, not too much. You will go from 2 par k, choose 2 to simply 2 par k. Remember, 2 par k, choose 2 is what? Something 2 par 2 k. No, it's a slightly smaller reduction. Okay. So, it's not a dubious statement. It is a reduction, but it's not a very significant reduction. Okay. So, like I said, this problem is very hard. So, you can't really make it polynomial or anything. Okay. So, let us see how to do that. It's very easy. What was my definition of minimum distance? Minimum over u comma v in C u not equal to v, the Hamming distance between u comma v. Okay, just now we saw the Hamming distance between u comma v is the same as the Hamming weight of u plus v. Okay. But remember, u is in the code, v is in the code. So what about u plus v? It is also in the code. So this is equal to some x which is in the code. Okay. So instead of going through all the u comma v's and then adding them up and ending back in the code itself, I can just look at the code words of the code and simply do a weight. Okay. So this becomes the same as minimum over x in C. The only thing I have to worry about is u not equal to v. Okay, u not equal to v translates as x not equal to 0, okay, of weight of x. Okay. So now the minimum is over only 2 power k minus 1 possibilities, but still it is exponential in k, a lot of computations have to be done, but it is not 2 power k choose 2. Okay. So it is a simple little observation that u plus v anyway belongs to the code. So you will be anyway doing the same computation over and over again, unnecessarily you can avoid some computations. Okay. Alright, so let us see some examples, quickly compute maybe the minimum distance. So I will restrict myself to, let us say, n equals 4, very simple cases. Let us start with k equals 0. Okay, k equals 0 is really nothing much to do here. So it is 4 comma 0 comma 0, right. So okay, so I should tell you what I am writing here. Okay. So codes are usually denoted nkd. Okay. So we will denote codes as nkd. Okay. So notation for what? Nk code with minimum distance d. Okay, so that is the notation. So for k equals 0 we saw just one code which was just 0 0 0 0, okay, and that is a 4 0 0 code. Okay, so that is not very interesting. So what about k equals 1? Okay. So we have several different possibilities. There will be 4 possibilities which are non-equivalent. I will list them out. Okay. So let us say G1 equals 1 0 0 0, G2 equals, sorry, where did I put 0, 1 1 0 0, G3 equals 1 1 1 0, and G4 equals 1 1 1 1. Okay, so those are the 4 non-trivial, non-equivalent possibilities for k equals 1. Okay, and what would be the parameters for these codes? 4 comma 1 comma 1. How did I get that 1? Remember, each of these codes have just 2 code words. One of them is all 0. I do not have to consider that in the minimum distance computation. The other code is what is in that row itself. So clearly that is just 1. Okay. So what about this one? 4 1 2, 4 1 3, and this guy is 4 1 4. Okay. So among these 4, which is the best code? Okay. Okay. Yeah, I mean, I never told you that having a large minimum distance is good, but looks like you have assumed it, and it seems like a good assumption. Okay. So maybe 414 is the best code among these 4. Okay. So let us take a few with k equals 2. I do not want to take too many of these codes. Let us just take let us say G1 equals 1 1 0 0 1 1 1 1. Simply take 2 just for comparison, 1 1 1 0 1 1. Okay, so here are 2 codes, k equals 2 there are obviously several others. I am not writing down. Okay. What about the parameters here? 4 comma 2 is easy. What about the third parameter? 2, right? Okay, so how did I get that? There are 4 code words in this code. The 4 code words are 0000, 1100, 1111. What is the fourth code word? 0011. Okay, clearly looking at it, you know that 2 is the minimum distance. What about G2? 4, 2, 1. Okay, so the code, if you find out, is 0000, 1110, 1111. The last code word is 0001. Okay. Okay, so now I'm going to throw out an open challenge in the class. You know, we are recording, but anyway, I think this is an interesting challenge. Okay, so what is the best possible minimum distance that you can come up with for k equals 2? Can you do any better? So for k equals 1, we were able to quickly see that there was one generator matrix that gave you the absolute best code. There was nothing else you can do. What about 4, 2?
2.
Can you quickly prove in your head, eliminate all the cases and show that 3 is not possible? It's not a difficult proof for 4, 2. You can never have a 4, 2 code which has minimum distance 3. Why? Yeah.
We need 3 codes with 3 ones each.
Yeah.
Which
So
is
you,
not possible.
yeah.
4C3 is not.
Yeah. So you can look at it. For 4, 2, 3 will not be possible. It needs some careful arguing. It's not too difficult. You can just exhaust all the possibilities. You have to have 2 G, right? 2 rows in G. Each row should have weight at least 3, right? Otherwise it won't have. So both have 3, right? And then when you XOR them, what has to happen? 2 of them will go off to 0. If both have 3, it has to overlap at least in 2 places. Okay, so that's a pure combinatorial argument, right? So this is where the combinatorics in coding will come in. Okay, so when you do minimum distance arguments, it will become a little bit more combinatorial. Okay, so and it's more painful. Okay, of course writing down subspaces and all is very easy. When you think in terms of this, even for 4, 2, it's so difficult. Can you imagine for a general NK how hard it would be to think of minimum distance? Okay, so it's a bit more complicated. Okay, we'll see more about these things later on. But anyway, hopefully you are convinced that answering the question of what is the best minimum distance for a given n and k is not very easy. Okay, so it's a bit more difficult. You have to do some calculations, think about it. Okay, so it's a bit non-obvious. Okay, I can ask you more difficult questions. For okay, 4, 2 is easy enough. If you go to like 1500, okay, n equals 1000 and k equals 500, right? What is the best possible minimum distance? It's a very hard question to answer. Okay, in fact, many of those questions are not answered till now. Okay, if you find an answer, you can become very famous. Okay, so think about it. Okay, so this is the difficulty. So already you're seeing minimum distance is a little bit more painful than what we thought before. Okay, so we'll see more and more examples, and it'll become clearer as we go along. Okay, any questions at this point? You're okay? All right. Okay, so that's all the examples I wanted to do with minimum distance, but I'll draw a picture of a code and minimum distance, etc., just to give you a feel for how it looks. Okay, so suppose you imagine that this big ellipse here holds all the this is a nice geometric view which is very useful. So holds all the vectors in F2n. Okay, right? Suppose you imagine this is the set of all vectors in F2n, and suppose you are looking at an nkd code. Okay, how many code words will there be? 2 par k code words, right? So maybe I put a star at each code word. Okay, so there will be 2 par k code words. Okay, maybe I should put one more star, make it at least a valid 2 par something. Okay, so you have these code words. Okay, how do you capture the d? Okay. You can think of the distance as Hamming distance, it is a little bit not same as Euclidean distance, but anyway you can imagine that that is the Hamming distance. What am I saying when I say minimum distance is d? The distance between any two stars is at least d. Okay, so that is what it means. Okay, so that is the picture that you should have in mind. Okay, so you have the set of all vectors, a few of the vectors are your code words, and any two code words are at least a distance d apart in Hamming distance. Okay. So, once again let me summarize, n and k are easy for most codes, when you describe them n and k will be easy. Okay. In fact, for some code descriptions k might be difficult, but anyway it does not matter. So, n and k are usually easy. Given n and k, if you ask questions like what is the best possible d that I can get, those questions are tough. Okay. They are naturally going to be tough because they are not algebraic, they are not linear algebra questions, they are combinatorial questions involving discrete objects, and these are naturally more difficult. Okay. In fact, many of these problems are NP complete. Okay. So, you can't hope for a simple answer, you have to imagine that difficult answers will come up. Okay. So, the next, but nevertheless what I should tell you is there are constructions available which given a d and a n try to construct a generator matrix or a parity check matrix for an NKD code. Okay. So, there are constructions available for a given d. Okay. So, it seems like quite challenging job, it is a very challenging situation, but one relationship which is very useful in controlling minimum distance is the following property of the parity check matrix. It turns out the parity check matrix and the minimum distance are related. Okay. So, it does not seem very obvious right now, but when I write it down it will be clear to you, and that relationship is very vital in the design of codes with a certain minimum distance. Okay. If I want to design a code with a certain guaranteed minimum distance, this relationship that I am going to write down between the minimum distance and the parity check matrix is vital. Okay. So, that is the relationship you use again and again to relate to design codes with a guaranteed minimum distance. Okay. So, what is the relationship? It goes like this. Okay. So, let me write it down, minimum distance and parity check matrix. It is a very simple relationship, but it takes some time to get your head around. Okay. So, let me write it down first and we will do a few examples and ask you a few questions, and eventually maybe it will sink in. Okay. So, suppose I have an NKD code, remember I am writing NKD now, previously we were writing NK code, now I am adding the D with parity check matrix H. Okay. Suppose you have an NKD code, parity check matrix H. Okay. What is the connection between D and H is what I should ask you, or what I am trying to prove. So, let us see what is H. If you have C being a non-zero code word with weight, let us say W. Okay. C is some non-zero code word with weight W. What does it mean? C, if you write it down as a vector, there will be a whole bunch of zeros, but how many ones will there be? W ones. Okay. So, everything else will be 0. What do I know about the parity check matrix and C? Yeah. So, H times C transpose is 0. Okay. Right. H times C transpose is 0. So, now let me write down the columns of H. Okay. So, the first time I am talking about the columns. Okay. So far I have never spoken about the columns, right, always it was about the rows. Okay. We are worried about the row space of G, which was the code itself, and the row space of H, which was the dual code. Okay. So, the row space of H was the dual code. So, that seemed simple enough, just linear algebra. Now, I am going to talk about the columns of H. Okay. So, let us say the first column of H is H1, second column is H2, so on. There will be n columns, and I will assume that in C you have W1s, and these are in the I1th position, I2th position, so on till IWth position. Okay. So, you have n positions in the code word, and there are only W ones, everything else is 0. The W ones occur at the I1th place, I2th place, so on till IWth place. Okay. So, what happens actually when I do this multiplication? Okay. Actually what happens is, if I think of these things as vectors, hi1 plus hi2 plus so on till hiw equals 0. Okay. So, what does this mean? So, let me state what we did just now. If there is a code word of weight W, what does it mean? There are W columns of H which add to 0, okay. Or another way of phrasing it is, there are W columns of H which are linearly dependent. Okay. So, that is the way to think about it. Okay. All right. So, the weight of a code word is this, implies that many columns of the parity check matrix are linearly dependent. Okay. So, now how will I characterize the minimum weight or the minimum distance of a code? Linearly dependent, right. So, okay. So, I should let me complete that. Okay. The minimum distance of a code is the minimum number of columns of H which are linearly dependent. Is that okay? Is that okay? So, from this we get this following relationship, which is an important relationship. Okay. So, let me put a few stars to denote that it is important. Okay. D equals minimum number of columns H that are linearly dependent. Okay. So, I gave you an argument, but there is a subtle converse which I did not really prove, which is important. Okay. So, the converse is also equally important. What is the converse? If there are W columns of H which are linearly dependent, then there is a code word of weight less than or equal to W. Okay. So, that also is something you can quickly show, it is not too difficult. Okay. So, once you show that, this equation becomes a equality. Okay. So, D equals minimum number of columns of H that are linearly dependent. Yeah,
So,
and all those
the
things will
rank
come.
is-
Okay, we will come to bounds on D and all that, but one thing I want to quickly point out is D is very different from rank. Okay. It is defined using dependence of columns, but dependence of columns is roughly the same as dependence of rows. It is not a big deal. Rank is the same, but it is totally different from rank. Okay. Oh no, it has no direct relationship with rank. Okay, convince yourself that it has no relationship. As we see more and more examples, you will be sure. Okay, there are some bounds using rank, but there is no equality relationship with rank. Okay, so you can't just compute the rank and get it. If you can compute the rank and get it, then it wouldn't be an unsolved problem. It's an unsolved problem, so it's a very difficult thing to answer. Okay, what is the rank? How would you define rank? Maximum number of columns that are linearly independent. Okay, so that is how rank comes. Okay, so it's a bit different. Okay, so here it's the minimum number of columns that are linearly dependent. Okay, you can have an H which has an all 0 column, which means your minimum distance is 1. There is one column which is linearly dependent, but still the rank can be full. Okay, so there is no direct relationship. So let me give you some examples. Okay, so you'll see how it works. Okay, so the examples are very illuminating. Okay, so So let us see the first thing I am going to talk about is d equals 0. Okay. Okay, when will d be 0? Okay, go back to this definition. Of course, d is 0 if oh my god.
No, if the rank, if the all the
So
row
remember
columns
once
are
again, there is
linearly.
no real relationship between minimum distance and rank. Okay, so there is no distance and no relationship
So if
between
all the
minimum distance
columns
and
are
rank.
linearly independent, then
So how will you have minimum distance 0? You cannot have minimum distance 0.
n has
It
to
will
be
not
less
happen,
than
because any non-zero code word will have weight at least 1. Okay, so it will not happen. Okay, there is no sense in saying d equals 0, because by definition k is 0. Okay, yes, k is 0 is the only possibility. Okay, is the only possibility. Okay, so for any non-trivial case it will not happen. So let us not worry about this too much, but anyway we can keep this in the back of our mind. Okay, so basically n00 code is the only possibility for d equals 0. Okay, you can take any number of examples. Okay, so the next interesting example is d equals 1. Okay, from a code point of view, I guess answering the question is very simple. You just have a weight 1 code word, there is nothing much to say. But from the parity check point of view, what should happen if you have d equals 1? Well, 2 columns, d equals 1 means what? 1 column is linearly dependent, so to speak. So what should happen? You should have an all 0 column. Okay, there should be an all 0 column in H. Okay, is that okay? So this is the only way in which it can happen. Okay. So the third question, d equals 2. Yeah, there should be some repetition in the columns. Okay, 1 column, 2 columns should be identical. Okay. Okay. What about d equals 3? Yeah, so that is the way it works, right. So d equals 2, how did I get this? 2 columns of H should be identical. There should be 2 columns that are linearly dependent. The only way that will happen is the 2 columns add to 0, or which means they are the same. Okay, so it's exact same statement to make. So for d equals 3, what should happen? 1 column equals sum of 2 other columns. Well, when I say sum, it is always modulo 2 sum. Okay. Okay. So d equals 4 onwards is a little bit more complicated. Okay, so d equals 4 maybe is not too difficult, but d equals 5 onwards is definitely more complicated. Okay, so there are so many other, it's not too difficult to write down, but you see it's not very easy to just see and understand. Okay, so only up to d equals 3 you can just look at the parity check matrix and quickly figure out something. Okay, beyond that it's more difficult. Okay, so you have to exhaust all possible cases. Okay, is that all right? So the next thing I am going to ask is, I am going to make another statement, you tell me if it is true or not. Okay, suppose I have an NKD code. Okay, here is another result which is interesting, NKD code with parity check matrix H. Okay, and if I take so what will happen to this? Sum of any d minus 1 or fewer columns will be what? It will be non-zero. Is that okay? That is the way to, that is another way of restating that same question. Okay, if you have d minus 1 or fewer columns, it will be non-zero. Is that enough? What does this mean if I have sum of any d minus 1 of fewer columns not equal to 0? Means minimum distance is greater than or equal to d. Okay, so what else should I have if I have an nkd code? There is a set of d columns which add to 0. Okay, so some d columns add to 0. Okay, both these conditions have to be satisfied if you want to claim that the minimum distance, or if you know that the minimum distance is d, both these things should be satisfied. It is not enough to just say d minus 1 of fewer columns do not add to 0. This only gives you a bound. This tells you that minimum distance is greater than or equal to d. This only tells you that. This makes the thing equal. Okay, you get the equality sign with this. Okay. So quite often a strategy to show that I have a parity check matrix which defines a code with minimum distance at least d is what? What could be a strategy based on what I wrote down? You show that any d minus 1 of fewer columns do not add to 0. Okay. So in that case your minimum distance will be at least d. Okay. Or if you want to put it in more general terms, you have to say any d minus 1 of fewer columns are linearly independent. Okay. So right now we are dealing with binary vector space, so linear dependence is the same as sum. If your binary becomes some other field, then you have to worry about coefficients also. So in that case you make it linearly independent, it is okay. Okay. So this is the strategy that is used in most constructions. What is shown usually is any d minus 1 or fewer columns are linearly independent in my H that I constructed. So that implies the minimum distance is at least d. Okay. Most of the very famous constructions use simply that argument. The actual computation of d they will just leave out. Okay. It is enough if I know that it is bounded. Okay. Sometimes there are some other ways of getting to the minimum distance, but this is the most popular method of constructing parity check matrices. Okay. So you construct a parity check matrix and show d minus 1 or fewer columns are linearly independent, then you are done. Okay. But remember, how many computations will this take if you have to show d minus 1 or fewer columns are linearly independent? Okay. Once you select a particular set of columns, finding linear dependence is very easy, just a question of rank. Okay. You do Gaussian elimination, you get the answer. Okay. On the other hand, how many such things you have to take? N choose d minus 1 plus n choose d minus 2. If it is only n choose d minus 1, one can argue it is still polynomial and just n par d, something like that, but n choose d minus 1 plus n choose d minus 2 plus n choose d minus 3, so on, and if d becomes some alpha n, this is going to go as 2 power alpha n. Okay. So that is going to be exponential n. Okay. So it is not a small number. Okay. You have to add it up and it becomes a very large number. Okay. So you have to do too many of these things. So it's whichever way you look at it, problem is difficult, but it is a good design tool showing that it is linearly independent. Okay. All right. So we have a few minutes left. So let us try and tackle this problem of constructing a H with a guaranteed minimum distance for some simple cases. Okay. So d equals 0, no point in looking at anything, there is no code. Okay. It is only the trivial all 0 code. Okay. For d equals 1, also one can argue it's okay. I mean, it's not too difficult. You can come up with the construction very easily. For d equals 2, maybe it's not so interesting. D equals 3 is a little bit interesting. I'll tell you why d equals 3 is interesting. It turns out d equals 3 gives you some some error correcting capability. We haven't seen it yet, but it turns out d equals 3 is important for that. Okay. If you don't have d equals 3, you cannot correct any errors. Okay. Since the course is about correcting errors, so we have to at least start with d equals 3. Okay. So let us see how to do this. It is not very difficult, you can do it very intuitively in a very simple way. Okay. So I want to construct, so construction of H with d, let me say at least, let me say d equals 3. Okay. So it is not too difficult. Okay. So we already wrote down what has to happen. Okay, so if you want D equals 3, D minus 1 of your columns have to be linearly independent. Okay, so you should not have the all 0 column, that is ruled out. Okay, and no two columns should be the same. Okay, but two columns can add to the third column, that is okay. You are willing to live with D equals 3, two columns can add to the same column, say add to some other column, that is okay, but you should not have identical columns. Okay, so now if I say I have R rows in H, okay, if I have R rows in H, so my redundancy is R. Okay, so n minus k is R. If I fix n minus k equal to R, it is an important thing to fix n minus k, because I am looking at columns and trying to figure out what I can do. So, you can fix n minus k and then ask the question, how large can n be, so that I can still maintain D equals 3, okay, right. Remember, how many different possibilities are there? Once I fix n minus k, how many different columns can I have? 2 power n minus k, 2 power r. I cannot have more than that many columns. So, n is clearly has to be less than or equal to 2 power n minus k. Okay. Now, out of this 2 power n minus k, what is ruled out? All 0 is ruled out, and the reason why I had 2 power n minus k is I do not want to allow repetitions. If I allow repetitions, it will go on and on, but then I do not want D equals 2, I want D equals 3. Okay. So, I do not allow repetitions. So, clearly the maximum I can do is 2 power r minus 1. Okay. So, I can have n, let us say less than or equal to 2 power r minus 1. Okay. In the extreme case, I might want to pick n equals 2 power r minus 1, in which case how will I fill out all the columns? Put all possible non-zero all bit vectors. Okay, seems simple enough, right? D equals 3 is not too hard. Okay, said D equals 3 is really not hard. It's an easy enough construction. Okay, there is, I mean, one can easily argue that there is nothing better that you can do. I mean, for a given R, you want to maximize n, right? Why would you want to maximize n for a given R? Okay, D is fixed and R is fixed. Okay, n minus k is fixed. The parity bits you are adding is fixed. Okay, anything if you maximize n, what will happen? Number of message bits is being maximized, which is good for you. I mean, it's good to have more and more message bits and fewer fraction of parity bits, right. So, you do not want to waste, you want to maximize the number of bits per, I mean, k by n has to be larger, so it is good to do that. Okay. So, it is okay. So, what about k? It is going to be n minus k, I mean, it looks like it is n minus r, right. So, if you pick distinct vectors here, it looks like it is n minus r, but you have to be a little bit careful about linear dependence, linear independence, right. If I pick n equals 2 power r minus 1, what will be k? Okay. So, for finding k, so what is the problem with simply saying n minus k equals r? Okay, so what is the problem with this equation? I have assumed what I have put in here is linearly independent. It may not be linearly independent. Okay, so I have to check that. Okay. As long as it is linearly independent, then my n minus k becomes equal to r, and then I can settle k very easily. Okay. If I put n equals 2 power r minus 1, okay, I can definitely argue that k is equal to n minus r. How will I argue that? I am putting all possible r bit vectors. So, what are the in particular what vectors would I have put? Yeah, the vectors in the matrix I would have put, right. So, 1 0 0 1 0. So, those things will clearly be linearly independent. So, the rank will be equal to r. You can argue k will be n minus r. So, okay. Okay, so let us see a quick example. Maybe at that point you will see what I mean by this. Okay, so now let me introduce the 743 Hamming code. Officially name it. Okay, so I am running out of time real quick, so I will just end here. Okay, So, we saw this before, okay. So, I told you also that it is called the Hamming code, but now you know, a little bit more about this code. What do you know about this code? The minimum distance is 3, okay. So, that is something you know. Okay, so there was a lot to chew on. So, let us stop here and we will pick up from here tomorrow.